Welcome to another very introductory topic, which is the Inscribed Angle Theorem and some simple introductory problems. So what I shall do is I shall first state the theorem, and then we'll just go through some simple problems. So today is going to be a very simple lesson, so let's get on with it. But it is very fundamental, and with the help of this we'll do some 2-3 very interesting theorems over the next 2 days. So let me get done with this. So you have a circle, a very well known theorem, so all of you would have seen this before, so it's just a quick recap. You have a circle, and you can either think of a chord or you can think of this arc. Now we will say that the angle is inscribed in this chord AB or arc AB, and basically we will see that it says the same thing. Now once you have a chord like this or an arc like this, you can think of the center of the circle and think of this angle. This is called the central angle of the arc AB, and this will be the measure of the central angle. The measure of the central angle is basically the measure of this arc. Now, what does the Inscribed Angle Theorem say? Any such angle is called an angle inscribed in the chord or an angle inscribed in this arc. So basically the endpoints of the angle lie on EB, and this point D could be anywhere on the circle. So for example, D could be here, or D could be here, or D could be here, and no matter where, what the Inscribed Angle Theorem says is that this angle, and this angle, all these angles, okay, let's call this angle as X. All these angles are going to be X by 2, which is half of the central angle, and therefore of course all the angles are equal. So once again, not only are we saying that all the angles are equal, we are also saying that it is half of the central angle. So let's look at some immediate consequences of this, very well known, but worth a quick recap. So let's just finish this off. Now another way of stating this simple fact is like this. So you have a circle. If the endpoints of the quadrilateral lie on the circle, let's call this quadrilateral A, B, C, D, then A, B, C, D is called cyclic quadrilateral, and A, B, C, D are also called concyclic points. Now let's see, what does the Inscribed Angle Theorem tell us? Something very interesting about the cyclic quadrilateral. Suppose this is the center of the circle, then let's say that this angle is 2x. Then we know from the Inscribed Angle Theorem that angle B is x. Let's say that this angle is 2y. Then we know from the Inscribed Angle Theorem that this is y. And now you can see here that 2x plus 2y is equal to 360, and that means that x plus y is equal to 180, and we just proved in a line that the opposite angles of a cyclic quadrilateral add up to 180, or they are supplementary. Now the converse is also true. In other words, if you have a quadrilateral and if it so happens that the opposite angles add up to 180, then you can be sure that that quadrilateral is cyclic, or the points A, B, C, D are concyclic. So this is one very well known, well used result. Here's another one that you must keep in mind, and it's very easy. Let me just draw it all over again. This is fairly easy, by the way, but it is important for you to keep this in mind. So suppose again I have a concyclic quadrilateral like this: A, B, C, D. Now we'll use the inscribed angle theorem. Now let's look at the diagonal. Suppose I have a diagonal like this and another diagonal like this. Now this angle and this angle are equal. That's very obvious from here, from the diagram. Or in the same way, this angle and this angle are equal because they are angles inscribed in the same column. So they are equal. So this is another property of the concyclic quadrilateral, that these two angles are equal, these two angles are equal. So, but I want you to remember the converse. The converse is true. We'll not prove it here. So suppose I have a quadrilateral A, B, C, D. Already we know one way of recognizing if it is concyclic, which is the opposite angles are supplementary. But if it happens that there is a diagonal like this, and you are able to prove that this angle and this angle is equal, then that is it. This is a cyclic quadrilateral. So please remember this other version of this, recognizing the cyclic quadrilateral or proving that A, B, C, D are concyclic. And of course, I want to repeat this, the converse is also true. Alright, so with this background, let us solve a few introductory problems in the so-called inscribed angle theorem. So I have with me the problems. Once again, I will insist that you pause the video and solve these. These are fairly straightforward, just to get us started in this very important topic. So let me take the first problem. The first problem goes like this. You have a circle and you take some arbitrary point outside the circle and draw two lines. Now what you have to prove is that this angle, let's call it angle A, okay, BC is a arc, and DE is also an arc. Now what you have to prove is angle A is equal to half of arc DE minus arc BC. So this is a very standard result that we use quite often in problem solving. Now I hope you got it. This angle A is half of this arc minus this arc. So that's what we have to prove, and maybe you can do this. Just involves a small construction line, and that's about it. So if you could just try it on your own, it will be interesting. But otherwise, let me just go ahead. Looks like the power has gone off, but maybe you can still watch the video. So now here's the construction line that is going to help us to solve this problem. I'm actually hoping that the power will come back within a few minutes. Let's just keep going. Oh, it's come back. Great. So let's try and prove this. This is just a construction line. Now, what you have to notice is that this angle is half of arc DE. Now that's pretty clear. And similarly, this angle is equal to half of arc BC. And we're almost done. Just remember that this is an exterior angle of this triangle. This is an exterior angle of this triangle, and therefore we can say that half DE is equal to this interior angle, this interior angle, that is angle A plus half arc BC, and I think that's it. A is equal to half of arc DE minus BC, and we are done with this problem. Alright, so this was easy, just involved this construction line. Now we are going to solve another problem which is very similar in spirit. So I just have to draw the diagram. Let me just go ahead. What you have to prove is very similar. So this time the point P is inside the circle, and again, okay, A. Then again you draw two arbitrary lines, and what you have to prove that angle A is equal to half of arc DE plus BC. This time it's plus. So angle A is equal to half of arc BC plus arc DE. Okay. So let me see. Possibly just another construction line of this sort might do the trick, because this is clearly half BC by the Inscribed Angle Theorem, and this is clearly half DE, and this is, oh my god, this is so easy, and this is the exterior angle. So this is equal to this plus this, and we are done. I don't think we need to explain anymore. Now I'm going to also finish this lesson with, I think, two more problems. So let's go ahead. Let me just state the problem, and I urge you to try it. So I'll have to refer to my notebook. Okay, this is a good problem, though it is a very standard problem. So here the problem goes like this. You have a angle B, A, C. Then he says that take some point P anywhere you like. So let's say I take it here. Then he says drop a perpendicular from P to this line. Let's call it X. And drop another perpendicular from P. Let's call it Y. Now he asks you to prove that this angle, I'm sorry, this is a badly drawn line. Let me just try again. Okay, he wants you to prove that this angle is the same as this angle. Okay, this is to be proved that these two angles are same. Actually, it's a very standard problem. Let me just quickly go ahead. I think what you have to notice here very quickly is that P, X, A, Y is cyclic. And once you realize that, you're done. Why is it cyclic? Because if you look at this angle is 90 and this angle is 90. So the opposite sides of this quadrilateral add up to 180, and therefore I said that the converse is also true. If the opposite angles add up to 180, then it's a cyclic quadrilateral. And once it's cyclic, I think I just told you that these two angles will be same because they are angle inscribed in the same chord. So I repeat, this is angle and this is another angle which is inscribed in the same chord of a circle, and there is definitely a circle passing through these 4 points, and because it is cyclic. Okay, so that's the end of this problem. There's one more problem, introductory problem, which is more of angle chasing, but I think the more interesting part about the next problem, introductory problem, is the statement of the problem itself. The actual solution is just, you will see, just figuring out a few angles. So you could try it for some time before we look at my answer. So I state the problem. It goes like this. you have a circle, and you have the triangle inside the circle. So basically the circle is the circumcircle of this triangle, and then you draw the bisector, external bisector of angle C. So this is the external bisector. This is the external angle and this is the bisector. Now this intersects the circle at point D, and the problem says that show that AD and BD are equal. Okay, so that is the problem. If you want, you can try it for some time and pause the video, but don't look at my solution up front. And I'm giving you a hint. It's just a matter of finding out a few angles. In this case, when we have to prove that AD equal to BD, we will try to prove that these two angles are equal. And once we manage to prove that these two angles are equal, then we are done. So first of all, this external angle is equal to angle A plus angle B of the triangle ABC. So of the triangle ABC, and therefore since it is a bisector, this angle itself is A plus B by 2. Okay, A plus B by 2. Now we are into the circumscribed circle. Which is the angle that is A plus B by 2, and you can see that this angle is A plus B, the whole thing divided by 2. Now all that remains to show is that angle marked there is also A plus B by 2. And how will we do that? Notice that this angle is Y. If this angle is Y, by the Inscribed Angle Theorem, this angle is also Y. But Y is nothing but angle B minus A plus B by 2. So B minus A plus B by 2, and this is nothing but B minus A divided by 2. So Y is nothing but B minus A divided by 2, and therefore this entire yellow angle is angle A plus Y, that is A plus B by 2 minus A by 2, which is A plus B by 2, and we are done. Because this is also A plus B by 2, that is also A plus B by 2, it's an isosceles triangle, we are done. This completes the introductory problems in this topic of Inscribed Angle Theorem, and now we'll combine many of the theorems that we have learned to do some really interesting problems in the next few classes. But meanwhile, I think you should be very comfortable with this wonderful theorem. Alright, that's the end of this lesson. Bye-bye.